Hey, thanks, Gautam. I just want to thank everyone for organizing this and say I really enjoyed the talks this morning. Today, I'm mostly going to be talking about the cost of privacy, which kind of came up a little bit in Adam's talk, so it'll be a little bit similar. And I'm only going to be talking about multivariate medians. These are my two co-authors. They were both supposed to send me pictures, and neither of them did, so they have to be pixelated today. And this one is Shoja, my PhD supervisor. He was actually supposed to give the talk today, so you got stuck with budget Shoja, which is me. And over here is Akash. I don't know if this is working. Oh yeah, there we go, it's just slow. Which is our other colleague, and they're both from Waterlit. Okay, so this is the outline. It's just going to be three things, basically: depth functions and medians, the exponential mechanism, and sample complexity, or cost of privacy. Okay, so multivariate medians, what are they? So suppose we want to estimate the center of some data set. So for this talk, it'll be endpoints in RD, where D is the dimension. And we want to estimate the center robustly and privately, which we might say is a private median. And so often there's, you would think of the coordinate-wise median, where you just go along the columns of the database and take the median. But there's actually some issues with this median. For example, sometimes it can be outside the convex hull of the data, and it doesn't rotate with the data if you rotate your data. So in stats, there's all of these other medians that have nicer properties. And one example of them is the half-space median, otherwise known as the Tukey median. And so there's a lot of multivariate medians, and then a large subset of them are maximizers of something called a depth function. Okay, so what is a depth function? So it allows you to define order statistics and outlininess and centrality in spaces beyond univariate, so in multivariate space. And so how does it do this? It gives all points in the space a centrality rating with respect to the sample, or if you want to look at the population level with respect to a measure mu. And so just to make it really concrete, you can take a point. Oh, sorry, I'm not used to this thing. Okay. Yeah, you can take a point and a sample, and it gives you just a positive number in this interval that tells you how central that point is with respect to the sample. And then you can alternatively write how central the point is with respect to some measure. Okay. Right, so let's look at a definition. So this is the most probably well-known depth function. It's called half-space depth. And this is the definition, but I don't think it's very intuitive at first. So I'm just going to cover this geometric definition of how we compute, or how we can understand the sample half-space depth. So suppose we have these 5 points, bivariate points, or bivariate sample, I guess, and we want to compute the depth of this point. One thing we might do is project the points onto this unit vector, and then we can look at the projections as a univariate sample and measure the centrality of this point we're interested in with respect to this univariate sample in this direction. So one way to do that is to take the center outward rank, and there's different ways of doing that. We're just going to choose this one way for half-space depth. And so in this direction, this point has center outward rank 2, which is pretty high. And then what you do is just do this for all directions. And then once you do this for all directions, you take the minimum center outward rank and divide by n. Okay, so it's just kind of looking at centrality over all directions is how you arrive at the depth value. Okay, so and then just to show you a picture, if you have a sample here, I think it's 40 points from bivariate Gaussian, this is the depth of 2 different points. So you can see this middle point is like very central, so it has depth almost at the maximum 0.5, and this one is kind of on the edge and it's very outlying, so it's going to have low depth of 0.05. Okay, so that is depth functions, specifically half-space depth. And then you can also take the depth of the sample points, and that's how you get ranks. It's kind of a side. Okay, so if depth measures centrality, then the obvious choice for the median is the deepest point or most central point. So often we just use the maximizer of the sample depth function as the sample median. And then the population median just maximizes the population version of the depth. So the sample depth function will tend to the population version. Okay, so obviously this first thing here is not private. So how can we do this privately? And at the time, the obvious thing to do was use the exponential mechanism, right? So you want to maximize an objective function. You think of the exponential mechanism. Now there's kind of like noisy optimization algorithms you could think of too, but this is kind of the first thing we thought of that made the most sense, I guess. So what is the exponential mechanism, if you've forgotten or you don't know? You construct this density like this, and you just have 4 ingredients that you need. So you need your privacy parameter epsilon, the sensitivity of the depth function itself, and then we look at this base measure as a prior on the median. Okay, and then what you do is you take one draw from this, from a density proportional to this expression, and that's your pure differentially private estimate. So the prior, just a comment on it, so you can take it to be an indicator on a compact set, which is kind of equivalent to clipping the data, which is like often done, or you can just choose, like, you look at it in a Bayesian way and choose like an uninformative or informative prior. And it's kind of nice because you don't have to truncate the data, but you can. And so that means we don't have to know the range of the data, which is kind of bonus. Okay, so we need to know, what do we need to know about this algorithm, or what should we study about it? So we need to know the global sensitivity, which is pretty simple in this case, but the main question is, what is the cost of privacy? So this is a private estimate, but is it good? And how does it compare to the non-private case? So this was our main research question. And we're looking at it in the form of the framework of sample complexity. So how many samples do you need to estimate your parameter accurately with high probability? And we're specifically looking at what we call the cost of privacy, or privacy accuracy trade-off, which is the increase from non-private in the sample complexity from non-private to private. Okay. And so how do we do this? We came up with this regularity condition that allows us to look at the sample complexity and derive a theorem on it, as well as this also happens to give us the global sensitivity for free. So we say that a function, or in this specific talk, a depth function, is kf regular. So k is a constant and f is a class of bounded measurable functions. If the depth function satisfies this inequality here, and it's kind of opaque, but the main takeaway is that you get a constant and a class of functions associated with your depth, and then you just prove this inequality. And then once you have that, oh yeah, okay, so then you can also look at this as a Lipschitz condition. If you view your like objective or depth function as a function of the measure, and then you use a metric that's based on your class of functions. But this is not super important. It's just kind of if somebody was kind of looking at it that way. But anyway, you get this constant k and class of functions f, and the k gives you the global sensitivity automatically. So if you satisfy this regularity condition, then you have that the function has k over n global sensitivity. And then our main result is that the accuracy of both the private and the non-private estimate depend on the VC dimension of this class of functions. So where this regularity condition came from is we kind of proved different things for a bunch of depth functions, and then we were able to unify it with this regularity condition. For example, the half space depth is 1h regular, where h is the set of closed half spaces in R. Okay, so I said earlier that the accuracy of the estimate depends on the VC dimension of f, and so this is going to be our main result, which is an upper bound on the sample complexity of both the private draw from the exponential mechanism, or the private median we call it, and an upper bound of the non-private median. Upper bound on the sample complexity of the non-private median. Okay, and it looks like this. It's a very ugly thing, but I'm going to spend the rest of the talk breaking this down and showing how we can apply it. So there's some regularity conditions you need on the measure in D, but they're very kind of, they're not super specific. Like we don't assume mu is Gaussian or anything like that. And so the result reads like, with probability 1 minus gamma, our private draw from the exponential mechanism will be within t distance of the population parameter if we have at least this many samples over here, okay? So I'm just gonna go now, I forgot I have the clicker. Okay, I'm just gonna go through each of these components of this theorem, and then we'll do an example. Just wanna check. Okay, I got it, I'm good. All right, so this result kind of breaks down into three convenient parts. So the part one here is the upper bound on the non-private sample complexity. So this is completely the sampling error, the non-private error we call it. And then over here is the effect of the prior in the numerator, and the you'll see the privacy parameter in the denominator in this term and this term. So these two terms make up the cost of privacy, and this term is the non-private term. I keep forgetting. Okay, so all right, so the first term is this alpha function, which is, so the sample complexity only depends on the error t through this function alpha. And what is this function? It looks like this. So it's the maximum depth you can achieve minus the maximum depth you can achieve if you're at least t away from the true median. And this is like in a population sense. So it's kind of bringing the distance between, in the parameter space, to the, you might say something like the depth space. So what does this look like? So this is the bivariate contours of the bivariate half space depth for bivariate, multivariate normal data. I've never said bivariate so many times. Oh my gosh. Okay. So what you'll see here is that this is the deepest point in the middle. And as we move away from the deepest point, the depth is decreasing. So you're getting less central, which makes sense for the normal distribution. And so then this first part is easy. This is just going to be 1/2. And then what we want to do is calculate this second term here. So we're going to look at all points that are t far from the median. So they're going to lie on this circle. And we want to maximize the depth around this circle. And it's just going to be at the point of greatest spread. So it's going to be over here, and it intersects at 0.4. So then you would just plug in 0.5 minus 0.4 and 0.1, and you get 0.1. So that is what the alpha function is. It's kind of like looking at how much the depth changes as you change the, I guess it would be parameter or axis value. Okay. So that is how the sample complexity depends on the error. And then the prior effect is just going to be the log of the inverse of the probability of being in a small ball around the median, which is kind of like a mouthful. But just know that it's just contained in here, and then we're going to come back to it in our example. And then one simplification is if you take a Gaussian prior with a misspecified mean, then this term is approximately d log d plus your misspecification error. So how far your prior mean is from the true median. Okay, so it's the prior. And then the success probability is going to be here and here. And often, so for the rest of the talk, we'll assume that like d is moderate to large. And so then you can take a really high success probability. So we'll look up here, it'll be 1 minus something exponentially small in the dimension. So that is, in our view, pretty high. And then so this term is just going to reduce to the dimension. And then lastly, I'll just remind you that we use epsilon as the pure differential privacy parameter, and it just shows up here and here. It shows up here, but it's not so much of a thing. We'll see. Okay. So those are the components. This is our main result, I guess. And now I'm going to show you how to apply this to something tangible. So we're just going to look at the half-space median, estimating it privately when the distribution is normal with mean theta naught and covariance matrix sigma. But in the estimation, we'll say we don't know it's normal, so we'll use the non-parametric depth median. Okay, so this is what we're trying to estimate. So in this case, the median for the population normal distribution is going to be the same as the mean. And we want to compare the non-parametric estimate to the exponential mechanism estimate with normal prior. Okay. So let's start breaking this term down now. So we can start with our general result and start substituting stuff in. So the VC dimension of H is linear in D, so we can replace the non-parameter term there with D. And then in the case of half-space depth, with underlying normal, this is what that alpha function I was talking about looks like. So it's going to depend on the largest eigenvalue of the covariance matrix. So the more spread your data is, the more samples you need to estimate, which makes sense. And it's kind of nice because if T is really small, then this is almost linear in T. So it's kind of nice for interpretability. Okay, so that's in there now. And then we're going to put our success probability we talked about and the effect of the prior. So we assume normal prior. So this is kind of what you get when you put normal prior in. So we get the effect of the mean over here and the effect of the prior variance over here. And we're just going to make one further assumption that our prior variance isn't insanely huge, so you can bound it by some large polynomial in D, and our error is not insanely small. You can it's not exponentially small in D, for example. And then we end up with this nice simple expression, and the effect of the prior is just in this distance between the prior mean and the true median. So the sample complexity will scale in the square distance between the prior mean and the true median, or the squared misspecification error, you could say. Just gonna check my time. Okay. So I'm going to rewrite it like this, so it's a little bit bigger. And so let's talk about the prior effect. So, sorry, there's two cases. So there's what we call prior far, which is if you're greater than root d log d from the true median, then the prior is going to dominate the sample complexity in that case, because the d log d is going to be bigger than this term and this term, if we're in a situation where your desired error level and epsilon are fixed. And then there's prior close. So as soon as you enter prior close, the effect of the prior on the sample complexity is, in terms of scaling in D, small. Okay. So this is what you want to have. And then so let's assume, for simplicity, we're going to now look at the privacy accuracy trade-off. So we're going to assume we're in prior close, and then we're left with this simple expression for our sample complexity of the median. So this is the upper bound on the non-private, on the sample complexity of the non-private half-space median under Gaussian data, and this is the upper bound on the sample complexity of the private median under Gaussian data. Okay. So then what's left is comparing or looking at the relationship between t and epsilon. So on this side, you have an extra alpha t, or error function, versus this side, you have the privacy parameter. So then what you can do, so if we recall, we can say, give some new notation at the end of the talk. So NP is the private sample complexity bound, and NP is the non-private sample complexity bound. And then you might want to call this. Then we can write this privacy accuracy ratio, where this is the amount you would multiply the non-private sample complexity by to get your private sample complexity. So it's the percentage increase in the non-private sample complexity you would get to estimate your median privately, given a privacy budget and error level t. So it's kind of nice and simple. And for example, if you can look at this with epsilon fixed and t fixed, then the private is only log d worse than the non-private. So it's kind of a very nice result. And so that's it for this example. So the takeaway is that the private sample complexity is only log d worse than the non-private if you kind of make those assumptions, like, for example, the main one is probably prior close. And what you might do is determine the, I guess it would be the largest epsilon you can use that ensures privacy, and then look at and your desired error level, and this would tell you how much more sample size you would need from a planning perspective, if you're willing to assume Gaussian data. But you can do something similar for non-Gaussian. This will just be different. And then, okay, so that's it for that kind of particular example on depth functions. But I'll just note that you can apply our sample complexity result to any objective function that satisfies that regularity condition. So any objective function you want to put in the exponential mechanism, you could check that regularity condition. And if it holds, you can use our sample complexity result to get an upper bound on the sample complexity for whatever you want to estimate. So then we have some other extensions for things to do with depth, which rely on exponential mechanism paired with proposed test release. And we can modify this exponential mechanism to estimate the private depth values as well, which people use sometimes for inference, like hypothesis testing. Okay, so now these are the issues. So the polynomial time estimates for these estimators is really difficult. The depth medians often really difficult to compute without privacy. So this is kind of, in my opinion, the main issue we're having at the moment. Like for example, the depth functions are not concave. So that is kind of unfortunate. And this prior close situation, you don't really want to have to assume that. So we're working on getting like a coarse estimate that just automatically calibrates you to prior close privately. And then always asking how do you get this appropriate value of epsilon to ensure some interpretable level of privacy. And then I'll just, our papers here, but I mean, we've revised it like quite a lot since then. So yeah, that'll probably be, we're going to update this right away. So this may not look like exactly what I presented, but it's there. And thank you.